this is pretty laid back, pretty chilled. So, like tonight, I went through and I picked 3 different questions. One of them is over like weak acids, Ka and Kb value, because it's been a while since you've seen that, okay? So that's that 2005 question number 1, starts with propanoic acid. Then I got 2006, that's dealing with Ksb in equilibrium, okay? And then this 2006 question number 3 is like a lab component, okay? And that's kind of what they always throw in, is something related to a lab. It's like you actually kind of know, it's kind of general knowledge type information. So generally how the format works is I give you all about 10-15 minutes to work through the problem. Then we go over it and see how you all did. So if you need a calculator, hopefully you all have that. If not, then we're screwed. But then if you need your equation sheets, which hopefully you all have, that's what you're going to have available to you on the test. Now, just a word of advice on the test itself. So, a lot of times what you will see is that, if I were you all, okay, and you're actually taking this test, I know y'all were stressed and you all are used to going, oh, let me work number 1 and then I'll work part A and part B. Take a second and look at the entirety of the problem, okay? Because a lot of times on these problems, they'll actually kind of guide you through it, okay? The other thing and this just happens, it's test anxiety. And this is why I refuse to try to predict how kids are going to do on this test. Because I've had kids that I would bet large sums of money, they would get like at least a 4. Okay, they do well in the class, phenomenal. They get on the test, they flip out, and they get like a 2. Okay? And I had one kid, he sat right back there in the corner. Most of the time, and he had some family things going on, he was working late, but he'd show up and he was just dog tired, okay? And a lot of times he would literally like kind of just doze off through class. And I didn't mind because I knew he was going through some rough times. And he took the test and I'm going, okay, well, I'll take the test, whatever. And he ended up getting like a 3 on the test, and I would have bet that he was just going to get a 1 because maybe he absorbed it through that way. So, but some kids just tend to panic, okay? Like they read the very first line of the question and they go, oh my God, I don't know how to do this. And they completely flip out for the entire problem. What you'll see is that, number 1, a lot of times they guide you through it. Kind of you do this and then you do this. And then what they'll oftentimes do later on, they'll start with something related to that question, but yet completely independent of it. So they kind of start you over again. So if you get through like the first 1 or 2 parts of the test and on a question, you go, my God, I don't know how to do any of this. Don't give up on it, okay? Maybe further on down, you do find something that you can recognize, like, oh, I remember how to do that. Now, here's another test-taking strategy that you can do. Let's say that you have part A and you have no idea how to do part B, or part A, and it's a calculation, okay? But you know how to do part B, but you need a number from part A, and this is acceptable. If you make a note to the graders, okay, and what happens, how this is graded, is that they bring AP chemistry teachers in from all over the United States. Well, last year it wasn't done collectively because of COVID, but usually they bring them all into one city. And they get them together in this big hotel conference room. And for like 8 hours a day, you are assigned a problem and you grade that problem, okay? Now, the mindset of these graders is that they want to give you points, okay? So it isn't like you miss points, it's like how many points can you earn? So let's say that you need a number for part B, but you don't know how to get it out of part A. If you make a note that says, hey, I've completely spaced off on how to do part A, I'm going to assume that the answer from part A is 5, okay, as long as it's somewhat reasonable. And if you make that note and say, I'm going to use this number in part B, and then I'm going to work part B because I know how to work part B. They will give you credit for part B, okay? But that's something that you would have to say. So just as a strategy on the free response questions, okay? If you don't know how to do the very first part of a question, don't give up hope. Read the entire thing, okay? Literally, no matter what, I would read the entire question. See where they're going to go with this, okay? See where they're going to go. Then tackle it, because most of the time you're going to have more than enough time to do these questions, all right? So usually time really isn't a constraint, but also put yourself in the mindset of the graders. They want to give you points, okay? Write neatly, okay? Lay everything out. You're trying to convey to them that you know what's going on this test, okay? Because they want to give you points. But you have to earn it. You just can't say, oh, the pH is 7 without any calculations to show that. So there's a balancing act. You don't want to show no work at all, but you don't have to show them that you know that 14 plus 7 equals 21. You don't need to show that off to the side. But they should at least have an idea of where you're going with this, especially on the calculations. If it's just something that you have to explain, hey, give a justification for it. And again, you don't have to write a paragraph, because put yourself in the mindset of these people that are grading this. They're going to do this for 8 hours a day for 4 days a week, right? They don't want to read paragraphs. They want to cut through the chase, So don't feel like you have to write a paragraph. If you want to be succinct, you want to be to the point, that's it. Now, it's just funny. Sometimes, like, kids have been known to, like, attach dollar bills to their tests, okay? And so what these guys, that's a true story. And so that they create, like, a tip jar, and at the end of each night, they'll typically go to a place that might sell adult beverages, and they'll take that money that they get throughout the day, and they'll use that to kind of defer the cost of beverages for everyone. So I don't suggest that you necessarily try to bribe them, but I'm just saying it has been done. Okay, so here's what I want you to do. I want you to try and work this first question on 2005. This is all about Ka values. So I'm going to shut up. I'm going to stop the camera and just work through it. And if you don't know how to do it, hey, that's going to tell you what you need to work on. So here we go.
Are those the papers that I need?
Huh?
Are those the papers that I need?
Yes. Just need 1 second.
Okay.
Okay, kids. So if on this first one, all they want you to do is just write the expression. So on that first one, all you have to do is write, oh, Ka equals your hydronium ion concentration times your anion concentration divided by the concentration of the acid. Okay, literally, that was with 1 point. That's all you have to write. Okay, that's it. Now, and this is going to play out large later on. And you'll see this when we get more into thermodynamics and things like this. So it's always products over reactants. So that's where that comes from in terms of a bigger idea, because you've got this acid, right, forming this anion. So, quick refresher. If it's a weak acid, in which situation does equilibrium lie? To the left on the Ha side, or on the right with the hydronium and the anion? On the left, right? This is like 98% of this is the molecular form. Very little of it exists over here. So what does that mean in terms of the strength of this conjugate base? Strong conjugate base, weak conjugate base? Strong. That's what makes it, and here's the dichotomy. The weaker the acid, the stronger the conjugate base, okay? That's the dichotomy between the two of them, all right? So this is overwhelmingly going to exist like this. So if they say, hey, sometimes they'll make you like draw like the molecular structure or things like that. So if they said, hey, what does this thing actually look like on a molecular form? The vast majority of that is going to exist as that acid. Very little of it is going to be the hydronium on the anion side. Now, So then, when you get to B, so they want the pH value. So, and everyone that grades this test will recognize a rice chart. Okay, they will all recognize it. So you go, okay, now you don't have to, but if you want to set up a quick rice chart, go, okay, here we go. So this is, they gave you that molarity, right? Oops, wrong one. Of 0.265. You go 0, 0, minus x, plus x, boom, old hat, x and x, okay? So, and I've never seen this happen. I'm not saying I can't necessarily guarantee that it is going to happen, but I've never seen it where you have to worry about subtracting of that x becomes significant, okay? The only time it's like this 5% rule. If your ionization is less than 5%, subtracting that x doesn't matter. So don't worry about like technically doing the quadratic and all this. Noah Hale, if you're watching this, I know you're disappointed that you don't have to do the quadratic, but just don't worry about it. So you just assume that that remains as 0.265, and then your pH, you're going to find your x. So your x value should be 1.88 times 10 to the negative third is your hydronium ion concentration, then which gets you a pH of 2.73. Cool with that? Okay. Now, if it had been a strong acid, how would you find the pH? If it had been a 0.265 molar strong acid, how would you find the pH? Huh?
Isn't it the pKa? Isn't it the negative log of the given molarity?
Yeah. Okay, first off, Mr. Carter, if it's a strong acid, is there going to be Ka value? No, because Ka values are huge, which means the equilibrium lies to the right. There are no Ka values, so there are no pKa values. If it's a strong acid, and you start off at 0.265 here, when you get done, how much of it is going to exist as this molecular form? None of it. That's what makes it a strong acid. So your hydronium ion concentration would be 0.265. Take the negative log of that, boom, there's your pH. If it had been a strong acid, would my pH have been bigger or smaller than 2.73? Smaller, because you would have had a higher hydronium ion concentration. Okay?
I wonder what you were doing up here still.
This is it, hanging out with my nerds.
Well, I finished up with the track meet and stuff, so.
Oh, God bless you.
How goes it?
It's going.
Yeah.
Alright.
It was admission night, and we got some good news in terms of admissions.
Oh, okay, so what do we know? I do want to know. Anybody gonna share?
I got into Cornell and waitlisted at Columbia.
I got into Cornell, Princeton, UPenn, and waitlisted at Yale.
Okay.
And then we're still waiting on Dartmouth, because they were having technical difficulties.
There's certain irony to that.
Yeah,
Okay.
Yeah.
Impressive, you guys. Congratulations.
Yes.
thank you.
Very
Yeah.
cool. I was just coming to see if we totally scared your niece away, or if she actually.
Oh, no, she was very excited. She said, she got done, she stopped by, she goes, my chemistry classes were never that exciting. My chemistry classes were so boring. So, yeah, you very much impressed her. Yeah, yeah. So, no, she was impressed.
We did our job then.
Yes, you did,
All
very
right,
much
you
so.
guys have a good
All right,
night. Good luck, everybody.
okay. Now, so there's your answer to B. So now let's talk about C. So what changes on C? What does it now become?
Buffered solution?
Now it becomes a buffered solution because now you're going to add the anion, right? But you still want that same Ka value. So quick refresher on buffered solutions. So you're still going to start off Ha turning into hydronium ions and anions, okay? Now here's what you have to decide. Because of the fact that this is going to reach an equilibrium, right? you can work in millimoles, you can work in moles, you can work in molarity. Because in this case, it really doesn't matter because all the volumes are the same. So what I would recommend is, and it doesn't make any difference, I work the problem in moles. I said, okay, so because you have the 50 milliliters of your acetic acid, of that molarity, you multiply those numbers together, you get 1.33 times 10 to the minus second moles. Okay? Now, if you want to keep that as molarity, in this case, it's going to work out to be the exact same answer, it doesn't matter. Now, here's a common mistake that's made. You got 0.496 grams of the sodium propanoate. So you have to, when you calculate that molar mass, even though it's just going to be the anion that you're worried about, make sure you divide by the total mass of that whole salt, which the molar mass is like 96 grams. So if you're going to work in moles, then come back here. So that's going to work out to be 5.17 times 10 to the minus third moles. That's going to be 0 minus x plus x, okay? So then, out of this, here's the whole kicker. So then on part 1, it says the concentration of your propionate ions in the solution. Okay, so the volume hasn't changed. So you just have to take that number of moles and divide that by the volume of 0.05 liters. So that answer to point 1 is 0.103 molar solution. Okay, that's it. Boom. That's all you have to do. Now, part 2 gets a little sketchy because it wants the concentration of the hydronium ions. So this now becomes X. So if you look at this in terms of Ka, and this is why, in this situation, this is why they actually started you off writing the Ka values, because, I'm going to use that later on. So that Ka is your hydronium ion concentration, which you don't know, times your anion concentration, which is 0.265. No, your acid concentration, yeah. Hold on. I work one step ahead of myself. Which is 0.103, and then divided by 0.265. Okay? So if you solve for x, you get 3.45 times 10 to the negative fifth as your molarity, which is your hydronium ion concentration. Now, step back for just a second. When it wasn't when it was not a buffered solution, notice that hydronium ion concentration is 1.88 times 10 to the negative third. Okay? When it becomes a buffered solution, look what happens to the concentration of those hydronium ions. So why are the hydronium ion concentrations so much less here as a buffered solution than it is as a non-buffered solution? Ms. Cornell.
Can you repeat that question?
As a buffered solution, the hydronium ion concentration is 10 to the negative fifth. Okay? As a non-buffered solution, it's 10 to the negative third. So that's an order of magnitude of like 100. So why are there 100 times less hydronium ions as a buffered solution than as a non-buffered solution?
Because the other hydronium ions bond with the anion. No, I don't know. They what?
The pH goes up.
I know the pH goes up, but why?
Because Ka is a constant, so when one of them goes up, the other has to go down.
Okay, that's the magic key. You have to produce the same Ka value no matter what. So initially, when it was a non-buffered solution, this was X, boom, because Mother Nature wants to reach that point of equilibrium. Mother Nature wants that Ka value, okay? Winner, winner, chicken dinner. That's the number that wants. So when you make it a buffered solution, and you increase the concentration of your anions, okay, then what has to happen to the concentration of your hydronium ions? Those have to go down because you're still going to produce the exact same Ka value. That's why your pH goes up, because you have a smaller and smaller hydronium ion concentration. Okay. Cool with that one. Now, this is a classic situation when you get down to like D and E. D and E, you really don't have to know anything about what happened on part A, B, and C to do D. I mean, you kind of do, but not really. Now, so when you get to this one, the value of K, you want to calculate the value of the Kb. Now, here's the kicker. You have to start off with this. So, you've got HCO2 minus, right? Reacts with water to form methanoic and hydroxide ions. Now, they actually were nice, and they basically told you what the reaction was. Okay? So, here's the deal. So, this is going to pull a hydronium ion from the water. So you're going to get H2CO2 plus hydroxide ions. Now, here's the deal. Because you're generating hydroxide ions, what's going to happen to the pH? pH is going to go up. If it's an acid, your pH is going to go down because you're generating hydronium ions. Okay? So that's going to be the whole key to this. Now, you want to calculate Kb, right? So to calculate Kb, that's going to be the concentration of the acid times the concentration of your hydroxides divided by the concentration of your HCO2. Okay? You got to know three things. Now, here's the deal. So when you look at this, they tell you that the concentration of hydroxide is 4.1 times 10 to the negative 6. So that's your hydroxide ion concentration. But what else is that concentration in? What else does that number represent? Yeah, it's also the concentration of your acid, because it's going to be in a 1-to-1 ratio. So they don't explicitly tell you that, but by virtue of the hydroxide, you also know the concentration of the acid. Now, what's another way, they didn't make you do this, but what's another way they could have made you work this problem? By making you do an additional step. So instead of giving you the hydroxide concentration straight up, what could have they done? If you were writing this test, what's another way that you could make them end up with that hydroxide ion concentration?
Giving pH.
Yeah, they could have given you the pH of the solution, then you could have found the POH, and then you would have found the hydroxide ion concentration that way. Okay? In this situation, they were nice. They said, hey, here it is. So you got that, and then calculate each of the following. You want the Kb value. So, and it's got a 0.309 molar solution of this, so you know everything. So your Kb value should work out to be 5.65 times 10 to the negative 11. Okay, so that's what you should get for that Kb value. So then, on part B, they want you to calculate the Ka value. So how are you going to find the Ka value knowing the Kb value?
14 divided by that?
Yeah, so this would be a classic situation. So let's say you have completely flipped out on how to do part A. It's like, God, I do not remember how to calculate Kb. But if I have my Kb, I know how to find my Ka. So this is a situation you could write, I don't know how to find the Kb value, but I'm going to assume that it's 1.0 times 10 to the negative 10. Make up a number. And then you can use that number then to calculate your Ka value. Okay, but you would have to explain to them. Now, if you say the Kb value is like 25, and they're going to go, you don't know jack about Kb values, and they wouldn't give you the point. But as long as it's a reasonable, what you would expect a Kb value to be, and you use it, so then your Ka value here, you do that math like Mr. Carter said, you get 10 to the negative 4th, okay? And then on C it says which acid is stronger, or E, which acid is stronger, the propanoic or the methanoic. Party girl, what do you have?
I said the one with the larger Ka because I actually did not get as far to get any numbers.
Okay, and that would actually work, okay? Yeah, but it says justify your answer.
Because it wants to ionize more.
Bingo, that's actually cool. So what you should actually see is that it's methanoic acid, because if you actually calculate the Ka value, then it has a larger Ka, so it ionizes more, and there you go. Okay? Got it? Good? Okay, now try the KSP problem, which is the one on the back side of that. You've actually kind of worked this problem on a test, so this one should go pretty quickly. Okay, now, remember with solubility, here's the biggest shift that you have to make. When you're focused on this, here's your beaker, okay? And everybody wants to focus on the precipitate. That isn't the story. The story is what's happening with the ions that are up above it, okay? So don't focus on what's on the bottom, focus on what's happening in the solution, okay? So, when this stuff wants to ionize, it wants to turn into Pb and 2 iodine. So make sure that you pay attention to that subscript. So on the first one, here's the story. All they want you to do is just write the equilibrium expression. So that's just your lead ion concentration times your iodine concentration. But what do you have to do with the iodine concentration? You got to square it. Okay? If there was a 3, you would cube it. Okay? Don't forget that. All right? Now, because this ionizes in a 1-to-1 ratio, so if you look at the information that you have, there you go. So on this one, you have to pay attention to what they've given you. So they've given you the lead ion concentration, which is at 1.3 times 10 to the negative third. So what's going to be your iodine concentration? Twice that, right? So that's going to be, this is going to be 2.6 times 10 to the minus third. So when you calculate that KSP, here's going to be your lead ion concentration, but then you've got to double that iodine concentration and square it, okay? So you've got to do both. You got to square it and double it. So now, because this stuff isn't very soluble, that's the whole point of it. Should your KSP value be a big number or a small number? Party girl.
Pass.
Ben, KSP values, big numbers or small numbers?
Small.
Small. They're not favored in the forward direction. That's why they're insoluble, which is why you have positive delta G's and you have negative E naught values, because KSP values are small. So if you do that, you should get like 8.8 times 10 to the negative 9th. Okay? Now, when you get to the next part, the whole most important word on part B is that it's a saturated solution. So what that means is that up there in that solution, okay, it's holding the highest concentration that it possibly can to generate that KSP value. It's saturated. Can't hold any more. Okay? It'd be like you walk into this room and there are people sitting at every table. All the chairs are taken. It's saturated. So party girl walks in and is like, I got no place to sit. So she's going to have to remain in solution because there's no place for her to sit. Now, then we're going to add 2 liters of water. It says, what are the molar concentrations in this? Now, here's the deal. Because it's still saturated, okay, it's still saturated. Even though there's 2 liters of it, what's going to be the concentration of your ions?
They're going to be the same.
They're going to be the exact same. Your lead ion concentration is still going to be 1.3 times 10 to the negative third. Your iodine concentration is still going to be 2.6 times 10 to the negative third. Because of the fact that it's still saturated, which means that it's still in equilibrium. Okay? Now, but normally, if it wasn't a saturated solution, that's why it's the most important word. If it wasn't and you doubled the volume, then the concentrations become half of what they were. But because it's saturated and all you've done is just prepared a new solution, 2 liters, it's still the exact same concentration. Now, when you get to C, now if you look at what's happening on an atomic level, here's this precipitate. You got lead ions, you got a bunch of iodide ions, right? And you got some water. So I'm going to add sodium iodide. Is sodium iodide soluble?
Yes.
Yes, why?
Sodium is always soluble.
Yeah, group 1 elements are soluble, right? So what's going to happen to the concentration of your iodide ions? It's going to increase, right? So Mother Nature is going to flip out. It's like, ooh, this is bad, right? I get too many iodines on here. So what's the only thing Mother Nature can do? What'd you say?
Decrease the amount of lead in it.
Yeah. So how she can? What's her only thing that she can do? Yeah, make more precipitate. Okay, she's going to make more precipitate. So to do that, because your iodine ion concentration is going up, you're to produce the same KSP value, that ion concentration has to go down because you still want the KSP value, and the only place that it can go is into forming a precipitate. Okay, so then here's the deal. So then on D, KSP, they give you the Ka value. Now here's what's important on D. The two most important words of all in D is that there's no precipitate. So we're going to mix this stuff together and there's no precipitate, which means it could be exactly saturated. It's holding just as many ions as it possibly can. And if you add any more, it's going to make a precipitate. So that's one option. Or it's just not saturated at all and it could hold even more ions. Now, this is a situation where you got 500 milliliters of 8.2, 500 milliliters. Okay? Calculate molar concentrations. This is the easiest question that you are going to have tonight. What's going to be the molar concentrations? Yeah, because you're going to double the volume, right? So the molar concentration of your barium ions is going to be 4.2 times 10, was it 4.2 times, I don't know, 10 to the negative 6? I don't even remember. Okay? And then your dichromate ion concentration is also going to be 4.2 times 10 to the negative 6. Okay? Because it's just going to be half as much. So then, where did that go? I just had it. There it is. So then, no, it's 4.1. It starts off at 8.2. It's 4.1. My bad. 4.1 times 10 to the negative 6. And there's your dichromate or chromate concentration. So then you can calculate your QSP, which is basically going to be that concentration squared because it's your barium times your dichromate, and you get a QSP value of 1.7 times 10 to the negative 11. And that is bigger or smaller than your KSP value. Therefore, guess what? You don't make a precipitate. Okay? All right, so the shortest one is last, and that's that one. We'll knock through this real fast. So this is kind of a lab question. There's not a lot of calculations to do. So give that a go. That just kind of tests your general broad knowledge of chemistry. You just say, do you want to know?
No, we didn't even say. She just said unprompted.
Well, I did say, and then she told Janine that she didn't want to know, and so then I deleted it.
Okay.
So,
Okay, so real quick, so let's kind of go through this because this is like a general knowledge thing. So let's start with that one that raises the pH to above 7. So what's potentially going to raise the pH above 7? The cations on these or the anions? So how will the anions potentially raise the pH above 7?
Forming an acid and creating relations.
Bingo. So if that's what's going to happen, right? That's what's going to happen. Which one of these is the conjugate base off of a weak acid?
CO3.
Carbonate, right? Because that's hydrochloric, that's sulfuric. So therefore, X has to be your sodium carbonate. Okay? Got that one.
Sodium hydroxide? Maybe, but it's in there.
So then, you add hydrochloric acid to it. Okay? Nothing happens. Sodium hydroxide to it, nothing happens. Oh, okay, well, maybe that could be your potassium chloride. And then formation of a white precipitate, well, if you look at that one, then when you add sodium hydroxide, so if you just have to kind of know, which you all have done labs on with magnesium hydroxide, so that means that's going to be your MgSO4. Okay? So then we just answered B. It says, write the chemical form of precipitate. Now, here's the deal. If you think compound Z is something different and you're not going to make a precipitate, then you did something wrong. Okay? So B is going to be that. So, and then we just answered C. Why does your compound X have a pH greater than 7? So you need to say something like the carbonate ion, CO3 2- is going to react with water to form HCO3 1- and hydroxide ions. Okay? Just say something like that. Then on D is describe the steps for preparing 100 milliliters of 1 molar sodium hydroxide from a stock solution. So this one you need to use like that, and this is just like the lab that y'all just did. Okay? So you got M1V1 equals M2V2. Right? So you've got your stock. Y'all just did this calculation. Y'all did this. Literally, you just did this. Carter? No, you did it the day before when we calculated the concentration of your acetone, iodine, and hydronium ions. You did this for the acetone lab.
I definitely did not write this down then. I may have done it, just didn't.
Just did it differently?
Yeah, no, just didn't realize that I.
Okay. So here's the deal. So you got a 3 molar stock solution, right? So that's your initial concentration times V1, and you want to end up with 100 milliliters of a 1 molar solution. So if you do the math here, you get 33 milliliters. Now the whole key to this is it says you have a 100 milliliter volumetric flask. Now this is a little bit picky because of the fact that when you do dilutions, if you're diluting an acid, you add acid to water. If you're diluting a base, you reverse it, you add water to the base. So what you would do is you would say, hey, I'm going to put some base in there, I'm going to add water until it's, then technically you would say, oh, I'm going to take the pipette and I'm going to add water until it's at the exact 100 milliliter mark. Okay, so you kind of want to mention all of those things. And then on E, so you got sodium carbonate, calcium carbonate, right? So here's the simple one. Calcium carbonate is otherwise known as limestone. Okay, is limestone soluble or insoluble? It's insoluble. What do you know about sodium carbonate? Soluble. So there you go. So calcium carbonate would not be soluble. The sodium carbonate would be soluble. You can also do a flame test. Okay, sodium is a bright orange. Calcium carbonate tends to be reddish in color. So you could do a flame test, or you could say which one is soluble. Okay, we're done.